There are two parts. Part A, I'm going to talk some basic aspects of clouds in general. And in the second part, properties of some monsoon cloud systems that is specific to the Indian monsoon. You can ask a number of questions about the clouds, like what is a cloud, why in so many shapes, how a cloud forms, why all clouds don't rain, because many times we see cloud but there is no rain. So there's some connection between cloud and rain. And how is the environment inside a cloud, because often we see from a distance, really you don't know what is happening inside. Then what is the role of clouds in nature? Then what is the multi-scale nature of the clouds? So among these, I'm going to touch upon basically the ones in the green font. And other ones I'm not going to discuss because of lack of time. Yeah, when you look at the American Meteorological Society's glossary and search cloud, this is what appears on their webpage. Cloud is a visible aggregate of minute water droplets and or ice particles in the atmosphere above the Earth's surface. Remember that ground fog is not included as part of a cloud in the EMS glossary, that is one. And second is that there is a clear distinction between cloud and precipitation. Cloud is one with which it doesn't fall down towards Earth. It is retained with the parcel. Cloud means in the air. It doesn't fall towards the Earth's surface. Once a droplet grows enough and starts falling towards the ground, then it's called precipitation. So precipitation is all liquid or solid. Remember, when you say liquid, it is the water drops, and solid means ice waves. Aqueous particles that originate in the atmosphere and fall to the Earth's surface. This is what the precipitation is. Then the rain is precipitation in the form of liquid water. Drops that have diameters greater than 0.5 millimeter, but actually you can come down smaller also. Anything which is not held up by the updraft and able to escape that and come towards the ground is called a rain drop. And if widely scattered, the drops may be smaller. Normally more than 200 micron, above 0.2 millimeters, that particle becomes a rain cloud droplet. Now, when you look at clouds in another way, actually it's a mixture. So in this mixture, it's the dry air is the major component with more than 97% is dry air. Then water vapor is 0 to 2.5%. 0 means it's not absolutely 0, but very small. And that is condensed water, either in the form of water drops or droplets and ice particles. Together we call them as hydrometeors. So that is condensed water. That is 0 to 2.5%. That is the typical composition of a cloud. If you look at the size, it is from few tens of meters to thousands of kilometers. Okay, that is the scale it occupies, large scale. And shape is closely related to the air motion in which the cloud particles are embedded. So when you look at clouds, when you go out and see the sky, you see different types or shapes of the clouds. And by looking at the clouds, roughly you can say that what is the atmospheric condition, especially in terms of the stability or in terms of an approaching storm. For example, when you see a very tall cloud, which we call as cumulonimbus, whose roots are in the boundary layer, and it goes all the way to the tropopause. And those cumulonimbus clouds form when the atmosphere is convectively unstable, one. And also, there is some large-scale, low-level convergence. If there is a strong subsidence, under those conditions, cumulonimbus clouds, they don't form. And on the other hand, are you able to see my cursor moving on the screen?
Yes, sir.
Okay, good. So when you look at these clouds with a flattened top, these are cumulus clouds. So they form because of the thermals rising from the surface of the Earth. And when the atmosphere is stable, they are not able to develop vertically. And so therefore, these are then is an indication of a suppressed or large scale subsidence in the atmosphere. And sometimes you do see nice patches of cirrus clouds. These are ice clouds, very high level, above 9 kilometers. And you see them scattered there. And when you see them, see their concentration increasing or density increasing, that is an indication of a cold front is approaching. This happens mostly during winter in a tropical country like India. But when you see that there is some cold front, maybe about 500 kilometers away, but within a few days, you may get bad weather. That is the indication. So in fact, clouds, when you start studying them and relation to the atmospheric condition and the conditions under which they form, they indicate health of the atmosphere. When I say health, it means roughly what is happening on a large scale. And what roles the clouds play. And one of the most prominent role which is highlighted is that they interact with radiation. Like for example, this the top photograph is taken by a satellite, uh, and the top is a moon, and you have stratosphere, which is more or less in bluish in color, and there is a thick dark layer that is a tropopause. Below that, you have a troposphere. So most of the whatever the drama played by the clouds, that is limited to the tropopause. Very few of them are able to penetrate to the lower part of the stratosphere, but not more than 1 or 2 kilometers above the tropopause. That is the restriction. And what clouds do, as the slide below shows, is that they reflect incoming solar radiation, and also they trap the terrestrial radiation. They also emit radiation. So therefore, these clouds, they play a major role in the radiation balance of the Earth, and that also, in a way, leads to the control of planet's average climate. Now, what is shown here is an INSAT picture taken on 24th January 2012. And of course, in January, you don't see clouds much in the northern hemisphere, most of them in the southern. But the brightest ones, what you see here, they are the coldest or the tallest clouds, the cumulonimbus clouds. The regions where you see this dark, they are completely cloud free. And the areas with in between, they are either shallow clouds or mid-level clouds. So when you add up all the area which is occupied by the clouds, they occupy about 50% of the sky at any given instant. Because of this, as I said, they play a major role in Earth's radiation balance. And within this, when you see, there's a small fraction of the total area where you have active deep convective clouds. These are the cumulonimbus cloud systems whose roots are in the boundary layer and their tops are close, reach up to the tropopause. So they are the ones which occupy the entire depth of the troposphere. And those clouds, they occupy less than 0.1% of the area, but they are the ones which are rain producing clouds on Earth. So therefore, they play a major role when it comes to the water cycle, global hydrological cycle. Okay, then when you see clouds, the drama is being acted in the places where you see these very white, very bright patches of the clouds. They are the places where you have this cumulonimbus convection or deep clouds. And there is a big, large area surrounding that, which is free of clouds or having shallow clouds. What role are they playing? That's one. And are the two regions coupled or they are independent? It turns out that whatever the deep clouds you see here, it is like a drama, the nature's great drama. And whatever you see in the background with little or no clouds, that is a place where the background support is given. So if you look at Hadley, remember Hadley circulation, there is rising motion in the tropical region and there is subsidence in the middle latitude areas. And the air which sinks there, it comes near the surface at the return path and they become trade winds. So if I look at this cartoon on the left, so when I see the cumulonimbus cloud, they take air which converges at the low level to the upper troposphere. And here, when you see the air at the surface, it is rich in moisture. And when you look at the total energy, it consists of thermal energy, that is Cp into T. Then you have this potential energy, Gz, plus you have Lq, that is the latent heat. And that kinetic energy term, which is V square by 2, is relatively small compared to other three components. So therefore, we often refer to as moist static energy or dry static energy. Dry static energy is sum of Cpt plus Gz. When you add Lq term, that is latent heat, it becomes moist static energy. And this moist static energy is the one which drives this cumulonimbus cloud. And when air moves from the surface to the top of the atmosphere, because of the cold temperature, it cannot, the saturation vapor pressure is so low that the specific humidity, the Q refers to water vapor concentration or specific humidity here, that becomes almost zero here, and then it diverges. So the whatever the air diverges from there, that is virtually very dry. And when it goes out and into the clear sky, then that it starts subsiding. Why it comes down? That's because there is radiative cooling. And it descends along the path of dry and warm and the dry static energy, because there is no moisture role. It is a stable atmosphere. Only way it can subside or come down is by radiative cooling, and driven by this radiation, the air subsides. So whatever the air subsides here, this is where you get clear sky conditions. And where you get this deep convection, this is your intertropical convergence zone. In between, these two are separated by a distance of several thousand kilometers. And that's where all these areas they correspond to. And as the air moves from the subsidence region to the ITCZ region, all along the surfaces, I'm taking the case of ocean. What it does is it interacts with the ocean below, picks up sensible heat flux as well as moisture, that's the latent heat. So when it's subsiding here, it is poor in moisture and also perhaps low in temperature. But as it comes to close to the ITCZ, it gains both heat as well as moisture, and there's a large change in the moist static energy. And therefore, whatever the regions you see here, as you come closer and closer to the ITCZ, there you can see that the clouds are becoming slightly deeper and deeper. This is what I said, shallow cumulus clouds who are not able to grow, they are in this subsidence region or in the trade wind region. And this distance is several thousand kilometers. This is of the order of few hundred to maximum thousand, if not more than that. Okay. So there's a large difference in the scale. You can also see here that there is no wide separation. So, but whatever the moisture that is there in all these regions, it ultimately reaches the ITCZ, and there it starts rising in this. So there's a big difference in the time scale also. For example, the air which enters the cloud base here, it reaches the top in about 1 hour, not more than that. A distance of about 15 kilometers is covered in 1 hour. But once it comes here, return path is not easy. It has to be convectively cooling. It is about 2 degrees centigrade per day. So it takes about 25 days to 1 month to come back from here to here. Okay. So, but whatever the air comes down here, that is the one which can feed the cloud. So the two are coupled. So if I have to make a cartoon here, one region we have a moist ascent, you have latent release here. Whatever the air is here, it reaches the upper troposphere in about 1 hour. Then that air comes out there, but once it has to come down, it takes about 25 days to come from about 100 to 200 millibar all the way to about 900 millibar level. And this is where the dry subsidence dominates, and it is driven by radiative cooling. And this is the one which is feeding the deep convection. So therefore, this entire system is called radiative convective system. Sometimes there's a balance between how much air goes up in cumulonimbus clouds depends on how much air subsides because of radiation. So if there's a change in the radiative properties of the atmosphere, for example, because of the climate change, then radiation may accelerate or decelerate the availability of moisture or moisture air to deep convection. What's available, that will pump up very quickly. But what constant here is this portion. It is the one which will control how much convection will occur in the future as well. And when you look at nature, it is amazing. So it has designed a very efficient energy transport system using physical properties of water, in particular its phase change. For example, when you look at near the surface, let's say this is the interface between the atmosphere and the ocean or a land surface. Across this, there is evaporation occurring, and it absorbs the energy. And once it becomes vapor, it is just like any other component of a gas, behaves like an ideal gas. As long as there is no condensation, then it just remains in the air, nothing happens. But once it starts rising in the atmosphere and starts condensing, this condensation and as well as freezing, that releases energy. And there could be a large time separation or space separation between these two. You will get evaporation in one place and condensation in another faraway location, maybe a week later. So therefore, nature uses this exchange or just the phase change of water to transport energy. And essentially, it's a renewable fuel for nature's heat engine, and it efficiently transports energy. Like for example, when you look at Earth's geometry, it is more or less a sphere. So equatorial region receives a lot more solar energy because of that angle effect. The polar regions, they receive much less energy. So on the other hand, the atmosphere in the polar region as well as in the tropical region, they emit long wave radiation. So when you look at the annual average, so what this figure shows is the annual average net radiation from South Pole to the North Pole. Equator is here. This is 30 degrees south, 30 degrees north here. So there is a deficit in mid and high latitudes. There is excess in the troposphere, and this has to be transported. And half of this transport is done by the clouds or the atmospheric circulation. Just to give you a glimpse of what is the energy exchange that or the energy which water vapor carries. This is taken from a paper which appeared in Oceanography in 2016, ERA Interium Climatology. The top figure shows the latent heat flux only over the ocean. The scale here is 0 to 200 watts per meter square. The red is 200. The bluish color means the low values. That when you have very high evaporation occurs between 10 and 20 south. And if you see the air, this shows 850 HPA winds, actually the surface winds, I'm sorry, is that whatever the evaporation occurs here, it goes all the way around here and comes to the North Indian Ocean and towards India. And in comparison, the bottommost panel, it shows the latent heat flux. If you see the scale here, -20 to +20. And the redmost here is about 20 watts per meter square. You compare this with about 200 watts per meter square. So if you see this ratio, most of the energy, which is excess energy from the sun, that is which the atmosphere takes, that is carried or taken away by the latent heat, especially over the tropical oceans. And now, we have seen that during monsoon, it rains over the Indian subcontinent. This is taken from the TRMM 3B43, that is the climatology, 98 to 2010. And what you see here is, this is the lower panel is during July, and the upper panel is during February. Places where you see green and orange and reddish colors, they are the places where you get more rainfall. And the ones which are white in color, they have little rainfall in that month. So the places where you don't have rain, they are the place where, of course, evaporation occurs at all the places. But here, evaporation dominates over precipitation. And during July, if you see, there is a rain band here and there is a rain band here. But if you see where the highest evaporation occurs, that's somewhere in this region, and there hardly any rainfall. All the rain moisture is carried away from here to here. It comes and rains over the Indian subcontinent, west coast, as well as over here, Bay of Bengal, this region. So when you see the distance it travels, this is about 6 to 7,000 kilometers. That is the kind of distance which energy is carried with no loss at all the way to the place where it starts ascending and then starts releasing the heat. And that's why it is a very efficient transporter of energy. Now, let's see a couple of animations that will give you a glimpse of that how these monsoon clouds look like. That is one. And also second thing is that when you look at Indian monsoon or the cloud system, they are part of global or planetary circulation system. They are not independent. I think you please remember that when you try to understand any cloud system locally, one has to look at the entire globe rather than just looking at that place. Let me go to those couple of animations. Remember, there was a heavy flood in Mumbai on 26 July 2005. It rained almost 100 centimeters. So this is where Indian subcontinent is. And you see the connected clouds here, that the cloud band extends all the way from Indian subcontinent to the Pacific Ocean, almost dateline. This is the planetary scale circulation. And you can also see the polar region here. You can see that this is each frame is separated by 3 hours, and there is a connectedness from the entire globe, both in the polar region as well as mid latitudes. And when you see this, this is a synoptic scale system. This is a synoptic scale system, but this entire cloud band, they are also connected, and that is a planetary scale system. So when you look at the clouds, they have a scale which is of the order of 10,000 kilometers. That is the connectedness of these clouds. And this movie was okay by Dr. T.N. Venkatesh from NAL. What he did was that he took inside it is meteosat IR data. He looked at the temperature and gave vertical extent, so it becomes a 3D cloud. And from June to September, which is 122 days, that is every 3 hourly, that's 8 images a day, that he compressed into 3 minutes. So entire drama of 2004 monsoon is played here. When you see this picture, all these are cloud systems which form over the Bay of Bengal. This is the Arabian Sea. Then this is the Tibetan High. And you see influence of strong Tibetan anti-cyclone over the Tibetan High over there. And just watch how complex this entire thing is. Clouds form somewhere, they move somewhere, they dissipate somewhere else. Okay. So when you look at clouds, they are a major players in Earth's radiation balance. They transport energy both horizontally as well as vertically. And precipitation is actually a byproduct of this nature's grand heat engine. And it is a source of fresh water on land. So in fact, whenever you talk of monsoon, we talk about water. And nature designed it to transport energy, but in the process, we are getting rain. And they also wash away aerosols, impurities, as well as chemicals which are released in the atmosphere. So they are very important to keep the air clean. Then they have very rich science, and they're a major source of uncertainty in weather and climate models. If you look at the present, all the climate models or even weather models, toughest challenge is how to handle these clouds, especially those cumulonimbus clouds, what we have seen. So when you have seen that inside picture where clouds were there all the way from India to the Pacific Ocean. So that's why we call it a multi-scale problem. The reason is that the particle on which water starts condensing, what we call as cloud condensation nuclei, their size is of the order of 0.1 to 1 micron. So if we express it in terms of meter, it is 10 to the power minus 7 meters. And even when there is a change in composition of the aerosols or CCN or the concentration, people say there are numerical simulation who tried changing the composition and seeing its effect on a cyclone. It turns out that one can modify the cyclones by changing the composition of these CCN concentration or the type. They can influence even a cyclone. So therefore, they look very tiny, but they can modify the rain. Then the moisture supply to the cloud comes from more than 1,000 kilometers. So it's of the order of 26. And all they are interacting. So if you look at the ratio of the largest to the smallest, it is of the order of 10 to the power 13. So the events or the processes which occur on the scale, which are separated by 10 to the power 13, they are interacting here. And that's what makes understanding clouds and its study a very challenging and interesting task. In between this planetary scale and this micron or drop scale, like raindrop are typically about 2 micron. To fall to the ground, they have to become 200 microns. The large of them are some 108 micron, 8,000 micron is 8 millimeters. Some of the hail is, for example, is bigger. They grow. And this entire growth, and when you look at the change in the volume or mass, that is more than 1 million. So they grow by a factor of 1 million in weight over a period of just 15 minutes. That's amazing, that growth rate. And in between these drops and the planetary scale, you have what you call as a cloud scale, which is of the order of 1 to 10 kilometers. Then you have mesoscale, 100 kilometers. You have synoptic scale, which is of the order of 500 to 1,000 kilometers. And these cloud systems, they form, grow, decay, and reborn. They propagate. So, and there are many, many challenging research problems. Having said that, now let's come back to the monsoon clouds. And as far as we in India are concerned, monsoon is synonymous with rainfall. Rain comes from the clouds. Cloud is a multi-scale problem. There you have CCN, you have drop, you have cumulonimbus cloud, in between you have storm, it's the cluster of cumulonimbus clouds. Then you have mesoscale convective system. Then you have synoptic system, like for example, monsoon low end depression, and you have planetary scale. All these are interacting even in our monsoon cloud systems. So when I look at the problem at all this, since there is lack of time, I'm only going to touch on few of the topics. You can use satellites. What are the modern tools for cloud investigation? You can have polarimetric Doppler weather radar. You have instrumented aircraft, distrometers that measures the drop sizes and also the fall speed. This is at the ground. Now, satellites, they basically measure cloud top temperature, especially when you look at the infrared brightness temperature. The diagram here on the left, it shows temperature versus height is measured over the Indian region. One in blue color corresponds to the sounding taken on a day when it was convecting, and other one is on a non-conducting day. You can see some inversions there. But more importantly, when you see these deepest clouds, they can reach up to 15, 16 kilometers. So the cloud top temperatures could be as low as minus 70 degrees centigrade or 16 kilometers. Then in the mesoscale system, you also have these annual clouds. They are slightly less in height. Their top could be in the vicinity of 10 to 12 or 13 kilometers of the order of minus 35 to minus 40 degrees centigrade. So therefore, by looking at the brightness temperature of the satellite, you can identify deepest clouds and also this mesoscale annual. Then you have radar. A weather radar, what it does is it sends pulses of electromagnetic wave radiation. When they go, the wavelength is such that they scatter when cloud particles are encountered. Those hydrometeors here, it's not the bright drops, but it is the precipitation particles that they scatter in the rally, and that return power is proportional to the sixth power of the sizes. So therefore, this is measured, the return power. From that, you can constitute a quantity called radar reflectivity factor. It is proportional to the sixth power of the drop diameter. It is called, normally denoted by a symbol Z, or equivalent radar reflectivity factor. And remember that rainwater content, it goes as raindrop size to the power cube, and the rain rate, it goes is proportional to fall velocity, that's W, into T to the power 3, that's the drop volume. W goes typically around 0.6 or 0.7, D to the power 0.6. So rain rate varies as D to the power 3.6 or 3.7. So this radar measures Z, and also it can measure the radial component of velocity. These days, other products are also possible. So it acts like a proxy for hydrometric concentration, rainwater content, and also rain rate in the clouds. Now, when I say system, in the atmospheric context, a connected entity identified by pressure field or convergence of verticity field or remote sensing products like brightness temperature or some other field, is from the radar. So you can study them using satellite. You can look at three-dimensional structure using radars. You can also look at the nature of the drops using distrometer. You can also deploy aircraft, which was done during the TypeX program by IIT Pune. What is shown here is an INSAT image taken in the month of August. And if you see the color scheme, the one which is red is about minus 190, that coldest, that is this portion. And ones which are in black, they're warm temperatures, and in between you have cold temperatures. So whatever is below 230, those temperatures are shown here. So the ones you see very darkest patch, those areas have cumulonimbus clouds, and the ones which correspond to this blue patch, that is the annual portion of the mesoscale convective system. So how is that defined a mesoscale convective system? As having a precipitation area of at least 100 kilometers in one dimension or one direction. About 75% of total rain is associated with MCS. Therefore, if you want to understand our precipitation, you have to understand the mesoscale convective system in the monsoon clouds. You can ask again here number of questions like where the MCS is formed, how they propagate, what is the relationship with the synoptic system, is there a diurnal variation, either land-ocean contrast, there's a number of questions can be asked. And some of this we tried to answer using, and they became PhD thesis works of problems of Gambhir in 2000 and Shailendra Kumar 2016, Kapil Dev Sindhu, he used DWR data, and Jayesh Bhat, he used again INSAT data. And these are some of the relevant papers you can find. Okay, one question is, where do MCSs initially form? So what these two plots show is the fractional number of cloud systems that are triggered per 1 degree by 1 degree area during June, July, August, and September months, and using a threshold temperature of 208 K. That's a very cold cloud, remember. And this is considering about 6 years of, this should be 13 to 16, that is 6 years of this INSAT data. And where you see this red patch is the region where more number of clouds form. And in this figure, whatever the color shade is there it relates to the fractional number of numbers triggered. When you see this white patch means very small number is triggered. When it red means more numbers are triggered. And there are also, you can see some contours or lines here. They correspond to orography plotted at 300-meter interval. If you see where the triggering of this MCS occurs, remember this is the Eastern Ghats of India. Most of the triggering occurs here along the Eastern Ghats. So orography does play an important role in triggering the mesoscale convective system. This is during 14 to 18 local standard time. That is in the afternoon hours. So when you go to the late night or early morning hours, that is 2 to 5 LST, this is the time the convection pattern completely shifts. There is very less triggering over the land and more number of triggering you see over the ocean. So there's a day and night contrast between land and ocean, the headway, that Bay of Bengal and Central Bay of Bengal. During daytime, it's the land. Same day, nighttime, you should take more convection you see over the ocean. Also notice that there is also difference in the scale. Here, it goes all the way up to 10. Here, it's only up to 3. So number of systems which get triggered during daytime very high over in this region. This is the work of Jayesh Pardare and Bhat. And so when you look at the diurnal variation of CS formation, one can look at the periods when there is large scale lower level convergence, which we call as active monsoon period. You can create as the wonder weak large scale low level convergence. On the left is how many cloud systems get triggered in the box shown here. This is the main monsoon zone. And this is IST, that is local standard time. This is midnight to midnight. This is noon. And this is a fraction of them. Again, if you see early morning and midnight hours, there's less number. And maximum number forms somewhere between 15 to 18 hours. That is the maximum. And including especially during week period, maximum formation late afternoon and early morning, there's hardly anything. On the other hand, when you come to the head Bay of Bengal, this is the box shown here. You look at the formation. There is, throughout the day, there is some activity, but you can see two peaks during break monsoon conditions. One in the early morning around 3 a.m., another one around 12 in the afternoon. But once land activity starts, then you get suppression over the ocean. And how cloud systems propagate. See, when you saw that animation by Dr. Venkatesh, you've seen that clouds are never stationary. They keep on moving. Then how do they move? Because when you see that move, it looks very complex. But when you start isolating these cloud systems and plotting on a diagram, then some pattern emerges. For example, if you take a month and identify westward moving, means in the mean they move to the west, or eastward moving, and plot them, then wherever you see this excuse me, filled circle, they are the starting point and this is the end point. So that's where that's the mean direction. That's how one individual cloud system has moved. And if you see the eastward moving, there are very few of them are there over the Indian landmass, and most of the eastward motion are southeastward that occurs over the ocean only, or in the foothills of along the foothills of the Himalayas. On the other hand, when you look at westward motion, they are there almost everywhere. Okay? So when you take average over 5 or 6 years, there is a pattern that emerges. So this full is 100%. If you look at westward, southward, northward, or eastward, then over land, essentially it's mostly westward. Most of the systems over land, they move westward. Over the headway, you have westward and southward. You can see here. The little eastward is there, a little bit northward, not much. And for the equatorial Indian Ocean, it is more complex. Like for example, when you look at West Indian Ocean here, cloud systems move to the east. On the other hand, if you look at the Eastern Indian Ocean, predominantly they move westward. So there is a difference in the way the cloud system move between the East and West Indian Ocean. So when you look at this entire picture, the cloud system motion is rather complex, but over land it is rather simple. It's mostly westward. Then what is the relationship with synoptic condition systems? Because we know that major fraction of monsoon rainfall on Indian monsoon is associated with monsoon low pressure systems, the LPS, like monsoon lows and depressions. We also see strong diurnal variation in rainfall. And we know that monsoon, most of the convective rainfall comes from mesoscale convective systems. Then what is the connection between synoptic systems and MCSS? This is what I'm going to just briefly show one slide regarding that. So what is shown here on the left is a homolar diagram. Time increases for two Julys, 2013 and 14. The bluish color, they indicate cold periods, that is the presence of deep clouds. And on the other hand, warmer colors, which is here, they correspond to clear sky or break monsoon conditions. And wherever you have this L1, L2, L3, L4, these are the low pressure systems declared by IMD. And this homolar diagram, what is done is there's an average between 18 to 22 degrees north. And what is plotted here is 65 east all the way up to 90 degrees east. Time is upward. And this we are going from left to right is going from 65 east to 90 degrees east. What you see is that left leaning strips, they all corresponding to propagating monsoon systems. They get formed or initiated somewhere over between 80 and 85, that's the Bay of Bengal, that region, and they propagate westward or onto the Indian subcontinent. And this is a daily average brightness temperature. When I zoom in one of these times, what do you see? Okay, this is a little busy. Let me explain what it is. Let's look at the first panel here, which is C. And whatever you see in the color contour, again, it's the brightness temperature. No, the scale is lowest is 210, the warmest is 250. And so wherever you see this blue patch, that's the place where you have the deepest clouds. And the axis goes from, it is a month of July again, from 8 July to 15 July, they're about a week's time. And when you see 85, 90 degrees, remember our Andaman Islands is somewhere around 90. So 85 is somewhere North Bay. And 80 is Chennai, that's here. Somewhere our land mass starts somewhere here, okay, where the monsoon enters India. And you also have these contour lines. What are they? So they are lines of constant vorticity, low level 850 HPA vorticity. Okay, so you have this vorticity, very high vorticity here. As you go away, the vorticity decreases. This is the region of low vorticity. This is the region of high vorticity, and this is the region where you have strong vorticity gradient. This is center of that low pressure system, and to the this is the west, this is the east. And where you see these circles, they are the ones what you call mesoscale convective systems, which are tracked using some algorithm, and you can see them here. In a given system, about 3 to 4 MCSs form. They form somewhere here, and they start propagating west. In fact, it is this portion which is very favorable for the formation of this MCS. Once they form, they propagate rather fast. In fact, they move about 8 meters per second. They move away from the sun. So if you closely watch, this is midnight between, and this is midday. So if you see here, around afternoon of that, the activity starts, they propagate west, and they dissipate here by the midnight. Next day, the place where they were left over, somewhere there, again the new activity starts, and they propagate west, they dissipate here like this. That's what happens. Now when you try to summarize what we observe in that, there is a systematic organization of cloud systems within the LPSS. Several large, long-lasting, that when you say long-lasting, about 6 to 9 hours, some of them last 12 hours, cloud systems predominantly form on the western side of low-pressure systems in the region of, this is low-level 850 HPA vorticity gradient, and propagate further westward with a mean speed of 7.5 meters per second. CSS get triggered in the afternoon in the region of high vorticity gradient, propagate westwards, and dissipate by midnight. So what happens is after midnight, land becomes no longer favorable for the triggering convection. Convection shifts to the Bay of Bengal. Okay, there it lasts up to about in the afternoon, about 12 o'clock, then again it comes back to land. So next day, new CSS form around the area where previous day CSS dissipated, and the cycle continues. That's how you get a mean westward motion. And CS propagation over the Indian land is mainly Chola. I think I'm coming close to almost 1 hour now. So I'll briefly describe one problem. That is where precipitation originates. Because we get a lot of rain. The question is where the rain originates in the monsoon clouds. And where it originates, it is different from deep convective clouds and also orographic clouds. There, because this mostly is a warm rain process, this turns out to be cold microphysics that dominates. And for this, what we do is we take the Doppler weather radar of IMD. This is Hyderabad, then Nagpur, Calcutta, also Patiala. We have Bhopal, so many places. IMD was kind enough to share this data with us. It was part of the CTCZ program and also Encompass program. And remember that weather radar detects mainly precipitation. So whatever you see in the radar imageries, they are all precipitation related. And what we have done is try to identify convective cell and see how it grows. And it is a very busy thing, but let me try to explain what it is. The one on the top panel here, rows, that you project the maximum radar reflectivity measured by the radar on a horizontal plane, that is this patch. Wherever you see red and orange, those areas have deep convection. And place where you don't have clouds, it is in the dark. And each panel is separated by 10 minutes. And immediately below that is a vertical section taken through one of these, what we call it, the storm. And here, if you see where that, this is one of those vertical sections. And the maximum reflectivity is less than 40. 10 minutes later, this was the developing, whatever you see here on the left of that bigger one. So there you see precipitation developing here. The reflectivity has increased. Cloud has grown up to about 12 kilometers in height. And as you go to the next frame, 10 minutes later, this cloud has extended further up. And also the region where you have highest reflectivity, it has started descended to the ground. So precipitation first forms somewhere here, then it falls to the ground. So when you study this picture in detail, the picture that emerges is that in the cumulonimbus clouds storm, hydrometeors are lifted to the upper troposphere by strong updraft. This is the process. The first, they are in the very small size. Because of the strong updraft, they go all the way up to 12, 13 kilometers. And once the updraft becomes big, or the drops, they grow to strong enough. Now they are no longer drops, they are ice particles, they start falling. And when they grow and start falling towards the surface of the Earth, this is what we call it now the initiation or start of precipitation. They grow by ice microphysical processes. And maximum jet or the reflectivity first occurs between 4 and 6 kilometers level. This is where the maximum reflectivity occurs, but the growth occurs above this. And this is the neighborhood of the melting band. So it turns out that when you look at this, all this radar data, the mixed phase or liquid there, when you say mixed phase, there, vapor, liquid and ice, they coexist. It's roughly in 0 to -20 or -30 degree centigrade range, play a critical role in the growth of precipitation. In fact, mixed phase region, 5 to 8 kilometer levels in the atmosphere, is like a hydrometeor production factory of the globe. So in order to understand monsoon precipitation and rain, we need to understand the microphysics and dynamics of this mixed phase region. Because in case you want to understand or you numerically models also improve the rain or clouds improvement, then one has to understand what's happening in this region. Because that's the place where major fraction of the rain is produced, then it starts falling to the ground. Just one, this thing, you can measure drop characteristics using distometer, and you can measure both the fall velocity as well as the shape, as well as the size. And often you might have heard a term like stratiform rain, convective rain, and also that stratiform and convective stratification. So this is measured by a 2D video distometer installed by me in Bhubaneswar way back in 2012. And when you see stratiform, you see small little drops. With the beginning of convective rain, you see the average drop size has increased here. and the number of small drops have increased, but the exposure time is not same, they are different. During peak convective stage, you see bigger drops, okay? This is 100 millimeters and this is 100. Like for example, this one is of the order of 5 to 8 millimeter in size. So when you sample this convective rain, which corresponds to active convective portion of the cloud MCS, you get, this is what you call as the drop size distribution. So this is basically the number of drops present between in the diameter range d plus delta d. When you multiply this number by the width of that interval, you get the actual number. It is a density because you divide by the width of that interval. So it essentially looks like this. It's an exponential kind of distribution. You can have 10 to the power 5 all the way to 10 to the power minus 2. That's very few large drops, a large number of small drops. This is a convective rain. When it comes to stratiform, which falls from the anvil region, you have only one distribution. That's exponential, very rapidly falling. Okay. This is my last slide. It is just a curiosity question. Like, you get a lot of monsoon rain, but if you ask a question like, how many drops are there in a liter of in 1 liter of monsoon rainwater? And what I'm showing here is, one is Bangalore here, and another Agumbe. It is next to Cherrapunji. This is the second highest raining place in India. Then also the west coast here. Very close to that. It is on the west coast. It's Surathkal NIT, National Institute of Technology. It was installed there. Distrometers is the data from that. So this is the data of about 2 to 3 years. What is shown here is Bangalore is continental rain. This is orographic, Agumbe, and this is coastal, Indian west coast. This is diameter 0 to 8 millimeters. You don't measure 0. It starts with around 0.5. And this is the number of particles which fall on the surface per meter square, and it is the average number of drops in different diameter ranges in 1 liter of rainwater. So when you see a large number of very small drops and a few number of these things, and on the average there are about 2.4 million that is on the west coast, and if you look at orographic rain, is about 3 million drops are there, and Bangalore has in between is about 2.6 million. So this is the number of water drops that goes in making 1 liter of rainwater. Okay, I stop here. Thank you, and questions, please.
Thank you very much, sir, for this informative talk. And now the webinar is open for question and answer, so participants can interact with Professor Bhat.
Excuse me, sir.
Yes.
Hello, sir. I am Achintya from first year Earth System Science. Sir, I just wanted to know that since in India, not many colleges offer an undergraduate degree in this field, as far as I know, in Earth Science branch. So even you have come from a diverse background of mechanical engineering.
Correct.
And even in our batch, there are a lot of people from different backgrounds. So what is a piece of advice that you want to give us so that we can excel in this particular branch that you may have used at your time?
When you look at, I came from mechanical, you are right. See, when you study engineering, especially mechanical, we study thermodynamics, we study fluid mechanics, we study radiation. When you look at atmospheric flows, it involves these 3 ingredients. They are the major ingredients. And I also handled instruments. I'm familiar with instruments. So what is needed is atmospheric is a physical system. To understand this physics of this, you need good background in physics, or even engineering if you teach, or even we have also students who come from basically what are the students we get there from physics. Sometimes we are engineers, and very few, because chemistry they don't teach enough mathematics because you need some strong maths. So you have students from maths background. So that is the typical background we have. So my suggestion is that when it comes to atmospheric science, it is an applied science area. Have your basics very strong. So go to either MSc Physics or a BSc Physics or Engineering, and then come as specialization as MTech or PhD level. That's no problem at all. As long as your basics are good, then you can manage that. Are you able to hear me?
Yes, sir. And sir, one more small question on the basis of the answer that you said.
Yes.
Currently, if there is someone whose basics are not that clear, so what should he or she do at this stage?
Read a lot of basic books.
Okay.
Yeah, because there is no escaping from reading basic textbooks. Okay, first read the basic textbooks, understand the concept, and then go to papers or specialized fields. That's better.
And sir, just last question, sir. In order to right now it's been about 2 months, so we have been covered some topics of this branch from the top. So in order to get a physical experience, so one option that we students have is doing internships at various industries. So could you suggest us some places in India where we could do our internships, or some good places?
See, industries, I don't know. Of course, here from IIST, the Space Application Center, they do allow national NAL, they do allow these internships. Other places, I don't know about the industries, because long ago we had invitation from Microsoft. You remember all these uh, whenever you switch on your mobile, always there is weather information, and they do need people experts in weather. Other place where they use a lot of weather information is transportation industry, including aviation. Then you have these defense labs, but I think entry may be difficult. So yeah, even IMD, they may be interested by all the Ministry of Earth Sciences institutes. They will be interested. So the places where you will have exposure to the actual this thing, what you call the.
Yeah. Thank you so much.
Good afternoon,
Hello,
sir.
Yes, good afternoon.
Sir, I am Gaurav Kumar from MTech second year, Earth System Science. Sir, since this talk was on monsoon clouds and related to monsoon rain events, so basically I wanted to know one thing. In India this year also, many extreme rain events occurred. A few places like in Rajasthan, Gujarat, and Mumbai. So, what are the basic cause of that extreme rain events during monsoon?
So if you remember that one animation I showed, July 2005.
Yes, sir.
That was case of extreme event.
Yes, sir.
Okay, when you look at the extreme event, invariably it is associated with a large-scale system.
Yes, sir.
Okay, unless large-scale conditions are not favorable, then extreme event won't occur. And one thing we have found about these extreme events is that in recent years, the numbers are increasing, not only at a grid point, also the spatial extent. So there are 2-3 papers by Akshaya Nikumana, my student,
Yes.
on these extreme events and the synoptic systems. In fact, you can look at that and read that.
Yes.
But actually, there are two things about this extreme. One is how much rain it occurs continuously. Okay, within 24 hours, if system does move, and it moves very slowly and essentially stagnant but without losing intensity, then in a given place it rains a lot. That is one. Okay. On the other hand, if the cloud system moves very rapidly, then what happens is you will get heavy rainfall for a few hours, but before it becomes flood-like situation, it moves to another place. Okay,
Yes.
then you don't get that place. Ultimately, it is related to the large scale conditions are very important in this causing the heavy rainfall.
Yes, sir. Thank you, sir.
Good evening, sir.
Yes.
I am Sam. So I have a doubt regarding in your one picture in your slide. So you show the areas of cloud formation in over the Indian landmass. So we saw a large cloud formation over the near the eastern Ghats, but not to very much along the western Ghats region.
Yeah.
Why so? Both have a very steep orography, but why we are not seeing much cloud formation over the western Ghats?
No, there is enough cloud formation over there. Only thing is the stretch is small because over the eastern Ghats, when you see, it is mostly over the Bay of Bengal coast. Okay. When it comes to, I don't know whether you're able to see my screen or not now. Because okay, because I logged out of that full screen mode. You have it to, what matters is the vertical structure of the atmosphere, thermal structure. When you come to the Arabian Sea side, okay, where the air comes from. At low level, it is south of the equator. When then it becomes that fine later jet, and then it bends towards India and comes. That is near the surface. But if you go 1.5 kilometers, 2 kilometers above, all these are dry and hot air coming from the deserts of Africa and West Asia, right? So it poses a very strong inhibitor for the formation of deep clouds. So only when you come very close to the Arabian Sea, the Western Ghats, then the ascent starts and you get this orographic rain. On the other hand, when you look at the Bay of Bengal, that dry and what you call stable air is not over that Bay of Bengal. It is conducive for convection most of the time. Okay, so therefore, when the orography also, although it is there, moment there is little scope for ascent, it can easily condense and form clouds. So therefore, you get more rainfall over the eastern Bay of Bengal and that Myanmar Ghats compared to the west coast of India. That is the main region. And also, if you look at the vertical extent of these clouds over the Western Ghats area, let me see if I can. The clouds are shallow, but they still rain a lot. This thing, but somehow warm rain process is very efficient over the Western Ghats. On the other hand, when you look at the vertical extent of clouds over the Eastern Ghats, that is much deeper. It is about 7 to 8 kilometers. Over the Western Ghats, about 4 to 5 kilometers. So there is a paper by Shailendra Kumar and Bhat in JES, Journal of Earth System Science, on this orographic rain, orographic clouds in Southeast Asia. We consider Myanmar region, then Cherrapunji area, that's Khasi Hills, Western Ghats, and compare them. We can look at that.
Okay, sir. So one more thing, like in the last 3 years, especially over the Kerala and along the west coast, so a lot of extreme rain events are happening, and some experts suggest that the cloud structures are being changing, like we are getting more deep convective clouds. So does that mean like our vertical thermal structure also changing, or what is the?
I don't know. We don't have measurements. That's the unfortunate part. But I think if you to understand, especially there's a large amplification occurs between the coast and when you reach the Ghats, and it is the duration and the intensity. It's the product of these two that matters for, especially for this when it comes to landslides and floods. And like for example, when I have this distrometer, one at north of Mangalore on the coast. In the July of 2018, it rained 300 millimeters there. And Agume, which is just 50 kilometers from there, it rained 3000 millimeters. There is an amplification by a factor of 10 between these two. Still, I don't understand what makes what made 10 that amplify by 10 factors. So we need a good radar there along the coast, and then we have to look at how this intensification takes place. So in the absence of data, the other things become speculations. That's it. So we need more observations, whether it is remote or in situ. But in the absence of observation, difficult to say what's really happening.
Okay, sir. Thank you.
Sir, this is Ashwin from Geoinformatics department. Sir, when we study precipitational drought indexes, so there are two major used indexes like SPI, Standard Precipitation Index, whereas IMD is based upon the certain threshold key for each state. They have this threshold. So to study the drought index, what is the correct way to use this threshold, or precipitation SPI index is the best way?
You have to ask some IMD person on this. Because these indices are developed as indicators for how much rain has occurred, whether enough rain has occurred or not. Sorry, I am not studied that. Okay, sorry.
Okay, sir, one more question. Sir, this is a little off, sir. Like chicken egg problem in this monsoon also. Do monsoon brings create the forest, or the forest creates the clouds and cause the monsoons?
Okay, over ocean, is there forest?
Not forest, but there are high algal blooms present there.
No, even absence of algal bloom. There is no algal bloom. Also, you get rain over the oceans, which are free of forest. Right.
Yes, sir.
For the rain to occur, all you need is low-level convergence and vertical ascent. So that is the thing. And vegetation is in response to precipitation. Okay. So, like for example, when you look at India, there's a lot of deforestation has occurred between pre-independent India and after independence, right?
Yes, sir.
But of course, there is a trend, but you don't know whether due to climate change or deforestation. Forest may alter locally, but main thing is that whatever the rain you get is controlled by the large scale circulation. Locally, forest will modify that. They will supply CCN. They will also modify low level convergence. So it does make local influence. That's what the local factor, you can consider local factor, but major factor is large scale.
Okay, thank you, sir.
Any other questions? Any other questions from participants? Professor Manchanda is there. So good evening. Could you hear us?
Yes. Is it Professor Manchanda?
Yeah, sir.
Yes.
So very good afternoon or now evening, Professor Manchanda. After a long time, I saw you on the screen. Good to see you. Yeah.
It was my pleasure. I saw you. It's a night for me, 9 o'clock.
Oh, is it? Where are you now?
I came to Australia and COVID stopped me going back. There are no flights to return. So I'm stuck here. So it was a very good talk. Actually, Punaram was kind enough to send me this Zoom address. So I was looking forward to listening to you because you are one of the experts on rain. So
that is a flattery.
My problem has been is that it's so highly variable. Probably a couple of parameters we are missing, which we are not able to find. It probably is related to solar index or something, which one has to feed in some way.
When you say variable, it is a function of time. At what scale you measure, temporal scale, that's
you see, like this 30 years ago when we were talking of the size of these systems were something like 5,000 kilometers, 10,000 kilometers. Now their sizes are increasing actually. Almost half the globe is under one system.
Yeah, right.
So that has been my worry that 30 years ago when we were teaching things, we were not saying the whole globe is under one system. Now it seems to be.
Yeah,
so
because
maybe something is causing it happening like this because it's not the atmosphere. It has to be radiation input only.
One is radiation, then there is also teleconnections, So that also, because earlier we were like, when Walker found out about this Walker circulation or that index.
Yeah, hydrological
so,
cycle.
hydrological. So that time he had some idea, but only in recent, after the satellites came, we are able to observe from sky the entire globe at high temporal and spatial resolution. Now we are
maybe
able
that
to
is the reason.
Yeah, and also we have reanalysis products. And it is a combination of these two, we have better understanding of these global connections. Before that, that cause and effect or this thing means there is causative, this thing relationship is difficult, but you can see correlations between one and the other. So they are all related, but which is driving and which is driven, I think that is difficult to say.
Yeah, that's the whole thing, because once it's a complex interplay between the two, driving and driven, and then driven decides who is driving.
Yes. Yeah, that is.
So any questions to Professor Bhat? Yeah. So just one information, Manchanda sir was my PhD supervisor. And
oh, is it? Okay.
Oh,
so I just wanted to inform my students, those who are participating and other participants. So I was really benefited from his rich experience at TFR during my tenure. So thank you very much, sir. And let me thank Professor Bhat on behalf of all participants and IST for taking this, for taking his time and for this wonderful informative talk. So thank you very much, sir. We'll be very happy to hear you again as part of this webinar, because we will be continuing this webinar, for as long as IST exists. So this webinar will be basically controlled and managed from now onwards by our student. So I hope that this activity will be continuing for the benefits of a student. So I really thank you again, sir, on my behalf.
So it was my pleasure, certainly, and also good to hear some of the questions and seeing Professor Manchandra and also Professor Chandrasekhar. Okay.
Yeah. Thank you.
Okay. Good night to everybody then.
Okay. Okay.
Thank
Goodbye.
you very much, sir. Thank you, sir.